All right, we're back. We are Game 2005 and also blank screen in the fall 2017 semester, and we are week 9, kind of officially, unofficially, part 1 of our broadcast. I want to talk about assignment 2 really briefly, and then move into the next topic that we're going to be talking about, which is all around circular motion. All right, that should be cut off, but sorry, it's quite hard to see. I only see your screen and not mine. So, yeah. All right, so what is assignment 2? It's all around.
Wait a minute, that's the same day as the new Star Wars movie.
It's not my fault.
Be done by then.
It's not my fault. Yeah. Funny enough, funny that you say that. I have some loot boxes for you. Speaking of Star Wars. Yeah. So one of the first things that that we're going to be talking about is, like in assignment 2, is all around. It's all around this stuff with Newton's laws, circular motion, a little bit of projectile motion, free body diagrams. All that stuff is what this is all about. So think about this. Consider a loot crate at the top of a frictionless ramp. If the mass of the loot crate is 11.5 kilograms, and the ramp has a rise of 3 meters and a run of 4 meters, then compute the following. And it tells you to compute the free body diagram, the net force and acceleration, and so on. Okay, so this is the kind of way it's going to be, right? Some stuff that you've seen before. Same format as last time when we did our assignment number 1. This is up on Blackboard. And that's the first one. The second one, well, maybe a little bit different. You've got over a completely flat surface, a thermal detonator. Those people like Star Wars, is thrown by a Wookiee, a member of the Rebel Alliance, towards a group of Imperial stormtroopers. The thermal detonator always leaves the Wookiee's hand. I don't know how he does this. Maybe he's got some kind of special tech. With a speed of 100 meters per second, and the thermal detonator has a mass of 3.2 kilograms. That's pretty heavy. Suppose that the stormtroopers are 500 meters away. What is the correct angle for the Wookiee to throw the thermal detonator so that it reaches the stormtroopers, right? So this is the kind of stuff we're talking about. This is projectile motion, okay? So this is the second one. And the last one, for those people who are watching, is you got a little R2-D2 here, right? And I couldn't figure out a better way to do this. It's a Ferris Wheel question. Sorry, guys, but can't mask it up with something nicer than this. Consider R2-D2 a droid with a mass of 30 kilograms riding on a Ferris wheel with a diameter of 25 meters with a velocity of 2.8 meters per second. Compute the free body diagram for R2-D2 at the exact top, exact bottom, in both horizontal positions. And remember to include gravity. So, so these kind of questions are the ones that you're going to be dealing with. Again, I'm looking for groups to do this. This should be done with at least a group of 2. I would accept a group of 3 for this thing. So if you work with a group of 2 or 3, please have a group member. This is not to be done alone. So if you try and do this alone, I will not accept it. All right, so please don't do that. Again, it's for a group of 2 or 3 people. So the details are up on Blackboard. I'm going to go over that with you again later in lab. If you have any questions, take a look at those of the assignment. It's posted. You have a couple weeks, giving you a couple weeks, so that's until December 15th when, like our friend here said, one of your colleagues, your classmates said, Star Wars, the 15th of December is going to happen, right? And the same day that Star Wars is coming out, this thing is due, right? So that's why I've got a Star Wars themed assignment for you. As you notice, there's only 3 questions. Yeah, there's only 3 questions with a bunch of little things, the sub points. So what I'm looking for is, don't split them up. Please don't split these questions up amongst yourselves and say, okay, so I'm going to give one to Corey. I'm going to give another one to James. I'm going to give another one to Emma as an example, and all 3 of them are going to collaborate and make an assignment. That would be a mistake. All right, that's not what I want you to do, because I really would like for you to all do them. To give you practice on on doing this stuff, because I think if you don't have enough time to do it, if you don't get practice, then, or a test, if you will, that we'll be doing before that time is going to be more of a challenge for you. All right, so That's it. So you had a question. Go ahead.
Yes, for assignment 1, I know we use Desmos for graphic that we.
You can use Desmos if you need to again, right? Any resources you need, I got your hand. You know, I'm okay with it. There's nothing to graph necessarily here. I'm not asking for you to graph. I am asking you to do free body diagrams.
Yeah.
So you could use a variety of tools for that. You could draw it by hand if you're a neat person, like a neat writer or whatever. You could also use a tool if you want to. If you want to use things like Visio or whatever, I don't mind if you want to go that technical. You could also just use a drawing program and draw it with a drawing program like Illustrator or, I don't know, Fireworks, GIMP, I don't know, whatever. Don't go too crazy. This is just for your knowledge, because during the test, I'm going to ask you to select the right free body diagram and say which one is the right one. And then if you haven't constructed free body diagrams by yourself, you haven't actually looked at them, then you look at them and go, I have no idea what Tom is talking about. And we don't want that kind of circumstance. So that's that one. Okay, what are from the back of the room? The back of the room had a question. My friend, tell me.
You said up to 3.
All right, I'll allow 4.
No, that's fine. Like,
How many you want? 5?
Okay, 5. Well, 5 is good. We can do 5.
No, it's going to be 3, up to 3. Yeah, 2 is okay. 1 is not good. 3 is fine. Please don't make it 4 or 5. That would be very bad. Because it's not that big. It's not like the assignment's not huge that you guys need to use 4 or 5 people, and you all have to do it anyway, right? So, la. I don't know if I can say that any better. So yeah, so 3 people, please max. Please work with at least one other person to do this stuff. You know, it's good. It's like pair programming. And no, there are no programming questions. However, here's what I'm gonna put to you. If you have a good, I'm gonna say this so yes, you're gonna be clear. If you have a good application for this that you want to write, like let's say for Logan, as an example, he's so gung-ho on writing code that he wants to write, I'm just using his name. You know, he wants to write code instead of answering a question. Give me a proposal before assignment 2 is due, right? And if it makes sense, I will allow it, okay? So I'm not going to say no to code, but I want to know who's doing it and what you're doing, right? I'm not going to say, yeah, I'll just accept code in the place of assignment 1 and 2 and 3, right? I may allow you to do one of the assignments with code, but I want you to tell me which one, and you need to propose a plan for how to do it that makes sense. If it doesn't make sense, I'll say no, right? Just that way, if you're, you know, and you can do it with Unity if you want to. Yes.
Can we get back our first assignment?
What about?
Can we get back our first?
You will, yeah, you will eventually. Sorry, I'm just inundated right now with catch up, right? So
my assignment 2 handed in eventually.
yeah, and if you're handling late, we'll have a big hug. We'll have a big hug session. No problem, Corey. I love you for it, right? Anyways, are we good? Are we good with this assignment number 2? It's due again in a couple weeks. I think it's reasonable. I don't think it's too crazy. Before then, the plan was that we're supposed to have a test. So we're supposed to be testing you on this stuff next week. I think I'm going to hold off 1 more week. I'm going to test you on the same week your assignments due. So it'll be like, and that would give you a chance to look at the stuff, the content. I would have finished this module with circular motion and everything else today. We're finishing that. And projectile motion and Newton's laws and all that stuff. And that way it'll give you a chance to start your assignment, do your assignment, then get tested on it. It won't be so bad. If I test you next week, you wouldn't have started your assignment yet, probably, chances are. So you have other stuff going on. What was that?
We have midterms on this.
Right. So that, you know, I don't want to kill you guys. So that's, you know, I'll give you a couple weeks. So we'll have that in a couple weeks, yeah.
Do you know if the math tutors in the library are going to know what they're talking about any of this?
That's above my pay grade, buddy. I don't know. I mean, I'm just a soldier in this whole game, right? No, I'm joking. I really don't know. But
we went to Woodstock the last assignment. And it was like only 1 kid who could tutor us and like give us.
Okay. So the question was, people who are watching remote, the question was, is there a tutor for math at the library? Is that what you said?
Yeah.
That can tutor you on this stuff. I don't know. I'm going to try and find out for you, I guess. If you want to send me a note, and then what I'll do is I'll forward it to Alex. Maybe he can assist as well. But yeah, I'm not sure. It's not that difficult. I mean, it's just based on what we've done. And a lot of the stuff that I'm gonna put on the test for you is gonna be pretty much the examples that I've shown you with different numbers, right? Like I said, yeah.
So is this, sorry, on the lecture or on the lab?
The test will be during lab time. All right. So on the test day, like that week of the test, I may or may not elect to have a lecture, only because people are going to be studying. I may give it a review day, you know, where you come in, ask me your questions, and then before we go testing, show me your cheat sheets and all that kind of stuff, because you're going to make your own this time around. For people who are retesting, there are a few people for different reasons that have to retest. I will hold it next week, the retest during lab. So if you're a person who's never taken a test before, or there's a reason why you have to retest, there's a good reason, documented reason, then I will hold it next week during lab time. So I will have your cheat sheets, the same ones I used before, so you'll be using those. And then some scrap paper that you'll be writing. Please bring a pencil and a non-programmable calculator for those people who are doing it again. Okay? All right, and that holds true for test number 2. When test number 2 comes along, it'll be a pencil and non-programmable calculator you'll be doing. I plan to do it on Blackboard. It won't be done here. It will be done during lab time, right? So that way you get your marks quick. Any other questions? I think you had your hand up again. The test? Yeah, just to give you some more time, right? Because I know some people are really suffering right now with everything. Yeah.
What's the second test going to cover here?
The second test, good question. So the second test is going to be covering projectile motion. So the stuff we talked about before we left, a little bit, not too much, but I got to cover that a little bit in our test. But mostly this week and last week, mostly that's the thing. This is basically 3 weeks of, or the content of projectile motion, Newtonian motion last week, and circular motion. Mostly is going to be on it.
Lesson 5, 6, and 7.
Yeah, all these things, yeah. And that makes sense, right? So that way it's not so crazy. It's on 3 chapters. That's what it's supposed to be. And same thing that's covered in on your assignment, right? So the assignment and tests should match, should be kind of in sync. And that's why I've made them that way. So it's not going to be too crazy. It will be worth 20% of your grade, not 15% like the last one. But again, expect probably not as many crazy questions. There will be fewer of them. And again, you'll be asked the same kinds of questions, maybe broken down into several multiple choice parts.
So it's lesson 5, 6, and 7.
Yeah. So for example, we're covering 7 now. Well, because lesson 5 was really a combination of, if I'm not wrong, projectile motion, if I'm not wrong, right? I have to look at it, but it's projectile motion in 1 and 2D. Last week's Newtonian stuff, and this week's circular motion, and that's it, right? So this circular motion stuff, before I begin like talking about circular motion, is some of the most confusing stuff that you'll see, only because they start applying Newtonian stuff we talked about last week to circular motion. And circular motion, of course, is always more tricky, right? Just like when we do things like anything linear on the line, right? For example, when we're doing things like linear interpolation, which is kind of, you know, there's 2 points and you want to kind of find a point somewhere between 2 points. Not so bad, right? You have some kind of t-value, some kind of transition, and you find a point between the 2 lines, and you can kind of compute that, right? But once we get into splines, right, or some crazy motion that we do with rotations and all that kind of stuff, anything circular, all of a sudden the amount of complexity goes up like 3-4 times, right? So, and then multiply that even more when it comes to 3D motion as opposed to 2D. So this is why this is some of the most difficult stuff. So again, we're talking about circular motion and some other applications of Newton's laws. I will not be talking about viscous medium stuff, all right? So some of the stuff that this covers, this chapter in the book covers circular paths, accelerated frames of reference, those kind of things, and also how to do projectiles in or objects through a viscous medium. And viscosity, you know, the idea of that is almost like, imagine we have some kind of volume that we're traveling within, and actually in real life we are, where even the air is kind of a sort of viscous medium, right? We have this, you know, air pressure, we have resistance, air resistance, and all that kind of stuff. It's nice. It's really nice, but it's not going to really make any sense for games, right? So we're not going to cover viscous medium stuff because it doesn't make sense for games, not because I don't think it's neat physics, right? And I wouldn't have covered it before either. It's not something that I'm chopping off or anything like that. It just doesn't make any sense. If you actually look through the chapter around this stuff, it talks about things like topics like terminal velocity, which is okay, but you can kind of figure that out. In a game, you just set terminal velocity, right? You just say terminal velocity is 150 pixels per frame or something like that, right? You wouldn't say, the idea though is important because what happens is with terminal velocity, when you reach some kind of terminal speed, the upwards pressure decelerates you, at the same time that the downwards pull from the Earth's gravity accelerates you till you find an equilibrium. And that equilibrium is there's no more acceleration. You're just traveling at the same velocity, right? So that's terminal velocity. And it exists for both liquids, fluids, call it whatever you like, fluids, as well as other mediums, right? So fluids, air is a type of fluid, if you think about it, right? We just don't perceive it that way because we're human beings, but we live in it, right? This gas that makes up our air, right? Same as fluids that we are used to, things like water will be a fluid. But there's other types of fluids as well, and they have a different viscosity. And so there's a different resistance as a body drops through a fluid, because of gravity. Again, nice physics stuff, lovely stuff, not applicable in my mind to games unless you're doing a physics simulation or something like that. Even if we do things like, swimming in water, if you have a character swimming in water in a game, you're probably not going to apply proper physics to that. You're probably going to have some kind of caustic effects of shaders to make it look like you're going through some kind of watery effect. You might have a different sound effect to give feedback to the player that you're inside the water, right? And there might be an entry and exit animation, but at the end of the day, you're not going to sink like a stone necessarily. You may, depending on the game. Some games just make you just plain die, right? If you go into water, you're dead, right? But I've never seen a game where it takes into account viscosity of the fluid. You're going to travel faster in water and slower in mud, or something like that when you're swimming through some kind of muddy water. And even if you do, they're just going to give it a factor. They're going to say, okay, it's going to travel half as fast or twice as fast or whatever. It's not going to be accurate because it doesn't make any sense. And the character wouldn't know anyway. You wouldn't know. How would you know, right? So I've never seen that. So that's why we're not going to cover it. All right, so what is uniform circular motion? There's two types of motion we're going to be covering, uniform and non-uniform. Remember, the word uniform is not about CG. It's not computer graphics uniforms. We're sending to the we're not using it to send it to the shader language. It's not GLSL we're talking about. We're talking about uniform as in the same. That's what it means. So uniform means the same constant speed that something is moving. And the example would be if we have we're going to try to figure out the acceleration because of uniform circular motion, right? You can break down acceleration, so-called centripetal acceleration, right? Centripetal. An acceleration of motion traveling around some kind of circular, kind of track or a spline, if you will. And usually we kind of look at velocity squared or over radius. That's what this formula is. It's a very useful formula, and we're going to see that in use as we go forward. So v squared over r, right? So that means if I went to the next part, which is, hey, let's take a look at this uniform circular motion from a force perspective, right? And we're not talking Star Wars, the force. We're talking force, as in what we talked about last week. Newtonian physics, right? Force is equal to mass times acceleration. Well, if we know that acceleration is v squared over r, we can just substitute that, and that's what they've done here. So basically what they're saying is, since force is equal to mass times acceleration, then force can also, when it comes to centripetal force or uniform circular motion, we can say that force is equal to mass times v squared over r, right? Or mv squared over r is the short form for saying that, right? And notice also when we talk about force, where does the force go? John, where does the force go if you look at this diagram? Look at the diagram. Where does the force go? You should look at, sorry? Look at the circle, and where's the force pointing to? The center, right? And that's what's happening. The acceleration, right? all the forces from the acceleration of the mass are aiming towards the center. So it's almost like when you swing around something that's on a string, right? The energy is going towards the center of whatever's accelerating the force when it's traveling in a uniform circular pattern. In other words, when it's not accelerating and decelerating. So when do we have that situation? Well, imagine if I take a rope and I tie some kind of weight onto it, a thermal detonator, yeah, or some kind of weight, and I swing it around above my head over and over again, right? As long as I can keep my hand moving fairly regularly, uniform, right? Then I have an example of uniform circular motion, right? Why? Because if I'm swinging it around horizontally, around the horizontal, the gravity is being compensated for, right? It's not going to fall down. It's not wobbling too much unless I'm really bad, right? Another example of that, uniform circular motion would be some kind of horizontal fan, right? A fan, something moving, that's something that's moving in a certain pattern. Even then, you can see a little bit of wobbling sometimes, especially if it moves faster and faster, because you know what? It depends on how it's weighted and how it's centered. But typically, when we talk here in this, from this perspective, when we talk uniform circular motion, we're talking about horizontal motion, typically, with the tension going along this, from the outer part where the object is the weight or the mass that's being accelerated to the center. Okay, notice that in this diagram here that you have in the arrow, let's see if I can actually get my cursor somewhere. Cursors. I don't know if I can get my cursor. And yeah, no, I can't see it. Let's bring it up. Yep, it should be here, but it's not. But anyways, oh, here it is. Oh, well, there it is. See this little circular thing? So you see that the motion travels around the circle, right? But the force moves towards the center, right? Okay, this is interesting. And notice you kind of say, well, when does this thing detach? When can I expect if I go faster and faster? There's a tension along this, some kind of wire or something that's holding this weight around as it goes around. And yeah, it's true. It can snap, and it will happen at a certain point. It's almost like there's a limit to how much tension, an average cable or string will sustain before it breaks and flies off. And when it does, it's going to fly off in a tangent, right? Exact tangent to the circular motion. Well, why? How's that? Well, we knew that from way back. Back in the day when we were, in the Stone Ages, when we used slings, right? I mean, the sling works exactly this way. You would take a rock or something, you'd basically, have a circle around your head, and then you'd let the rock go, and it would go in a tangent to the circular motion. And so what am I doing? I'm actually accelerating this rock faster than I can possibly throw it, right? Because I keep on accelerating, and then I let it go. And when I do, it spins away on a tangent. If I'm talented enough, this sling will actually be very deadly. So uniform circular motion. So that's one type. The other one is this idea of a conical pendulum. Okay, so conical pendulum, what does that mean? It means a cone shape. You have one end of the one cable, the end of the cable is attached to a ceiling, as an example. And what's happening is it's not moving back and forth like a regular pendulum. It's actually moving around in a circle for some reason, okay? And you can imagine there's these old games, maybe some of you may have not known, some older guys like me, maybe Corey too. Sorry, Corey. But in the schoolyard, they had these like poles with like, I don't know, a rope and a ball, tether ball, right? And some people don't know that because those things don't exist anymore because they're dangerous. You might hit another kid or something, I don't know. Right, but back in the day, it was okay to hit kids. I mean, no, it's okay to use the tether ball, and no one complained too much, right? But this is the same idea. You have a pendulum on a string, right? And you hit the tether ball, and it kind of swings around, and it's smacks the other kid, I guess, or it's who can do it faster, who can do it better. But the idea here is the same. You have this tether ball, it's tethered on a string, and it's usually not on the ceiling, but on a pole, and then it goes around in this conical shape, a cone shape, because and again, this is another example of uniform circular motion because it's happening across the horizontal. All right, where we get into, and now you can see that the formula is different. It depends on if I want to find the velocity, how fast the ball is traveling around using this conical shape, it's usually the square root of the length of the ball times gravity times sine of theta, right, which is the angle that it's away from the center of, during its rest position. The rest position being straight up and down, right? So whatever that angle is, however far I can get it, multiplied by the tangent of that of that angle, and then you take the square root of all that, like I said, and you get the velocity, which is kind of a neat formula. And for us, would we ever use it in a game? I'm not sure, but I mean, I think might be some uses for something like that when you're making a puzzle game. Again, will I test you for this? I probably won't give you a conical pendulum necessarily a question on an assignment. And there's not a lot of crazy applications here from that perspective for you. All right, how about motion in a horizontal circle, right? This is what we've been talking about. So some kind of horizontal motion, and you have this idea of a tension that can support the mass, and you want to find the velocity, the speed that corresponds to the maximum tension that the string can hold, right? So the faster you go around a circle, the more chances you're going to fly off in a random direction, right? And it has to do with this idea of the total tension times the radius over the mass. So what does this mean? That means the greater the mass, right? That number gets bigger and bigger. Then the velocity is going to get smaller and smaller, right? Because it's heavier, right? Smaller mass means faster, right? And that makes sense for the same tension. All right, so that's what that formula is all about. You also have this idea of, now this is applicable to games, okay? So I would take a look at this. You make a car game or some kind of car simulation, and you have some kind of car following a track, a flat track we're talking about right now, right? So there's two kinds of curves, a flat curve and a banked curve. So this one's the flat curve. So you have this idea of static and kinetic friction. And we didn't really go into that much detail. I told you probably not going to test you too much on static and kinetic friction and the differences. The thing to note, just to reiterate the stuff we talked about in lab, is static friction, and I think Corey was asking this question last week, Ks versus kinetic friction, right? Or dynamic friction. You called it dynamic friction, right? Ks versus Kd, so static friction, is Ks. So what is that? It means it's the friction that's going to stop you from getting going. So before you're actually going, there's almost like a block, something that's preventing you from getting going. The friction is stopping you. And what we do is we take this coefficient of friction, static coefficient of friction, multiply it by the normal force, which is the force tied to how much gravity is pulling down your weight. So it's directly related to, or directly proportional to the amount of mass that you have that you're trying to push, right? Then there's this dynamic or kinetic friction, right? And then kinetic friction, so that's Fk, Fs, or static friction, Fk for kinetic friction. And that's when you're already moving, right? So when you're already in motion, right, you have a friction trying to slow you down, right? So here we're talking about static friction. And the static friction means that's why it's mu or mu s. What it really is saying is this, that on a horizontal flat curve, static friction is the thing that's stopping you from flying off in a random direction, right? It's the friction on the road, right? And the less the static friction, so Fs or mu of s, right? Then the easier for you to slide off into oblivion and fly off the road into a bank, into a ditch, right? So that's what's keeping you there. And so when we want to compute the total velocity for a car banking across a flat surface, we take the coefficient of friction, right, that we're dealing with, concrete, so mu of s, multiply it by the gravity, right, 9.8 meters per second, and then multiply it again by the radius of the curve. So whatever that radius of the curve is, we're going to take that into account too, because the rounder the curve is, the more difficult it is for the car to stay on the road without flying off into a ditch. Yeah. The inner radius, right? So that's what you're looking at, right? So it's from the radius. It's the radius from where the car is on the track, right? So if you're closer, it's the inner radius, and if you're in the outer lane, it's the outer radius. Wherever the car is, right? Yeah, so that's how this works. Notice that we have the normal force, right, that's pushing the car up, but in this diagram we have the static friction that's actually is the thing that's pulling the car in towards the middle of the road, right? So saving your life, basically. Friction is saving your life here. But we can't depend on drivers to do that. So what do? We create a banked curve. And banked curves, like for example on the 400, anyone travel on the 400 from the 401? It's a terrible drive, it's a terrible ramp there. And that's why they have those rumble strips, vroom, 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 to try to wake you up. Because when you go around this curve, man, if you don't control yourself, boom, you're flying into some other car or whatever, right? Anyways, they have this idea of a banked curve. Most ramps that come from the highway or go to the highway use a banked curve. And what they've done is they've calculated that if I increase the banking, almost like I'm rotating it across, so it's not a flat curve anymore, it's banked so that way it's towards the center, so that way you don't fly off. And so what happens is you can increase the speed, right? And if you notice here that depending on the angle, you can find the angle of the bank based on v squared over the radius times the gravity, right? And then you take the inverse tan of theta to figure out the angle if you want. So that's really the idea here. Now these are designed with the idea of friction equaling 0. What does that mean? That means that you're on a bank curve, and so for here in Canada, imagine we have lots of snow and ice. They make bank curves to help you. Otherwise, if it was a flat curve, woo, we'd be done in an ice storm or something, right? Even on a bank curve, it's pretty bad. But at least it's better. It makes it easier for us to navigate across curved surfaces with the car. All right, so I'm not going to talk too much about this, but I just want to talk about the idea of, this bank curve. And one thing to note about the bank curve, which it says here, is the angle's independent of the mass of the vehicle. So it doesn't matter how heavy the vehicle is. The bank curve is going to help you go around the curve. Because notice in the calculations, if I go back, there's no mention of the mass of the car, right? So velocity has nothing to do with the mass of the car. There's no mass of the car here. It has to do with the angle, and that's good. That it kind of almost like we make the mass of the car moot, right? We don't care about that so much, right? Which is good. It means like larger vehicles like trucks can go around a bank curve and most likely survive if the drivers are awake. That's why they have the rumble strips. Right? Ferris wheel example. This is a very popular way of defining this is where uniform circular motion is happening. An idea with when you have vertical, this is on the vertical, which is very rare, right? This is the only example where there's uniform circular motion on the vertical. Because typically this is not the case. Well, the other one, what's another example of uniform circular motion on the vertical that you can think of? Something that's really fast, hint, hint, right? No one knows. A propeller, that's a really great example of that, right? You get a propeller, right? And the propeller, what it's doing is it's pushing air. That's what it's doing, right? It's using Newton's laws, right? For every action, there's an equal and opposite reaction. That's the third law, right? And it's using the propeller at a different angle. All the blades of the propeller are different angles to push the air back away from the plane so the plane can have forward momentum. We'll talk about momentum next week, all right? But that's really what's happening. That's how a plane moves forward, because this propeller, from the angle of the blades, pushes the air back. And the faster the propeller goes, the more air gets pushed back, which causes the momentum of the plane or the velocity to increase. Yeah.
Okay, so for that assignment, it's basically you're adding gravity and the velocity if it's both going down.
Well, the forces are different. So depending on where you are, and that's a good question. Thank you, Corey. You're leading me into the next point, which is when you have still uniform motion here, because it's being controlled by a mechanism. It's not being controlled by my hand.
It's not a rock.
Right? Yeah, it's not a rock anymore. It's because of some mechanisms controlling the motion, right? But we can say that there's two different kinds of forces. There's one at the top, right? Imagine if you're on the top. There's forces that are pushing you away from the Ferris wheel because you're going to try and, the car is, it's almost like you want to fly off the Ferris wheel, right? This car. At the same time, you've got motion pulling down, right? The gravity, that's what's pulling you down. But it's different at the bottom. The bottom, you have more forces going towards the center, right? And at the same time, it's almost like more in equilibrium at the bottom than it is towards the top, right? There's also two other conditions. One where you're traveling on the right side. If the wheel is moving towards the right, right? So it's moving in a clockwise rotation, right? Then you can know that there's forces pushing down. As you move down, the forces are, the motion is moving down, and then the gravity is pulling down. So there's double the amount of forces in that position for each of the cars than there would be for example, on the other side of, on the other horizontal, where we're kind of, instead of moving down, you're moving back up the Ferris wheel. Then you can see that there'll be motions, there's energy going up, but there's motion pulling down, right? So there's less energy going on the left side than there is on the right. And one of your assignment questions asked you about that. So it kind of gets you to kind of did a little bit of research and try to understand how this uniform motion works when you have a mechanism, right? So Ferris wheel, I could have used a propeller again for the assignment, but I felt the propeller is too difficult because of the speed and everything else, because we haven't covered a lot of the stuff that you need. So Ferris wheel. All right, and yeah, and it talks about this idea of there's two forces, one for the bottom of the loop, what happens at the bottom, and they give you a little formula for the bottom, and they also give you a little formula for the top, and the formulas are different because what's happening is you have on the bottom you have more forces pushing downwards, right? As an example, 2 forces pulling down as you go towards the bottom, and then on the top it's different. You actually have 1 force pulling down and then another one pushing up. This is the normal force, but you're right at the top of the wheel, so you're not going to fly off. It's actually probably a position where there's not as much tension going downwards, and there's a little bit more tension going up. Okay, so kind of weird the way these things work, and again, I invite you to take a look at that. It's one of your questions in your assignment. All right, so now let's talk about something else. Let's think about when we're transitioning now from uniform circular motion to non-uniform circular motion. Why is that? Imagine if I have a ball moving on a circular path, but this time it's on a string and it's being propelled by a human, right? There's no way, it's very difficult for you to have uniform circular motion on the vertical, right? As well as there's different forces pulling at you. In the horizontal, I'm doing my sling. If I have a sling bullet, right, and I'm kind of having my sling go on the horizontal, the normal force that I'm projecting is kind of compensating for the downwards motion of gravity, right? But from a vertical perspective, if I'm swinging this way, there's more energy as I'm coming downwards because I have my swing. I'm accelerating this string on the way down plus gravity. So there's a different. We say it's non-uniform because the forces are non-uniform. And the speed also is not the same everywhere inside this this system. So like it says here, the speed is at the minimum at the top, and as you come down, it's the maximum at the bottom. So what is an example of non-uniform circular motion? Bowling, right? You have your ball at the top, right? And then as you come down, the speed becomes maximum. And depending on how people have this great technique for bowling, if they can time it properly, you can get a very, very fast speed to get yourself a strike, right? So that's vertical motion, but non-uniform. And they actually talk about here from this perspective, it's a different formula for non-uniform circular motion than it is for circular motion that's uniform, like a Ferris wheel, right? And you can see that we're using this mv squared over r minus gravity, mass times gravity at the top. And then at the bottom, we're adding gravity because you're right at the bottom. So actually, there's more forces at the bottom. So there's more speed at the bottom than there is at the top, right? You're with gravity at the bottom. You're against gravity at the top. All right, that's what's happening with non-uniform circular motion. And the book goes into quite a bit of detail around this and how to get the sum of all forces and where do they point. They don't point towards the center anymore, right? Like you do with uniform circular motion. Notice that you're getting 2 components of motion, right? You've got a tension, right? And you also have this idea of you're getting kind of the force towards your the center. There's force towards the center. There's also force, almost like a tangential force, that's tangent to the circular motion. You've got that as well, and then you get that sum of forces. What you're doing to calculate that is you use Pythagorean theorem to figure out that resultant force, the vector that you're moving in, right? All right, so that's really non-uniform circular motion as a very high level, right? They give you some more examples here about how gravitational force plays a role in changing this. Now, if we were using some kind of vertical motion that was non-uniform in another environment where there wasn't gravity, then it would be uniform, right? Because gravity wouldn't be in play. Yeah. Sure, I can do that. Yeah, so this is an example again of I'm getting the sum of all forces, right? And then I'm taking the sum of the forces towards the center and the sum of the forces towards the tangent to the curve that I'm traveling on, right? That sounds familiar. We can almost use calculus for that, tangent to the curve, right? And then you get the resultant force when you use Pythagorean theorem here. All right, let's move to this one. So again, like I talked about, there's these different forces at the top and the bottom of the circle. Tension at the bottom is maximum. Tension at the top is minimum. Why? When this is just for tension, not for velocity. Why? Because it's increasing. Because I've got double the amount of forces. I'm not only projecting downward, but I'm also being pulled by gravity. All right, here's one I'm not going to talk about. It's called fictitious force. All right. Okay. Why is this even here? Right. Well, we do feel, I'm not going to really go into it in a detailed perspective at the lab. And the reason why I'm not going to go into detail in the lab is because we don't really use it in games too much, right? What is it? Well, imagine if it's this idea of this accelerated frame of reference, right? So if I accelerate an object in a car, you don't feel any forces because like I talked about this last week, because you're inside the car. Your frame of reference is, you're inside the system. So you don't feel anything. But if we round a curve, as an example, right, then you're going to get this idea of, centrifugal force, right, like in a centrifuge, right, that pushes the occupant to the outside of the car if I'm going around a curve. And this is what they call fictitious force, because there's not really a pulling or pushing going on. You're inside the car. Now, if you were locked into if you had a seatbelt on, you probably wouldn't feel it as much. That's why we use seatbelts. However, you do feel on a tight curve, you do feel yourself pulling to the outside of the outward way of the car. If I'm turning towards the left, some kind of leftward ramp, you're going to feel forces pulling you toward the right because, and this is what they call fictitious force, this centrifugal force that's happening, right? Now, am I going to get you to compute that and all that kind of stuff in this course? No, I do want you to know about it, however, and that's why I'm mentioning it. Just like I mentioned, moving through a fluid. You should know about that, the idea of how the real world works. But from a games perspective, I just don't see a lot of applications too much, unless you're making some kind of really weird marble game where, I don't know, the marble was on a track and you were accelerating the marble over and over again. Then you probably could use this idea of centrifugal force to push the marble off the track, right? Then the other one is Coriolis force, right? So again, you've got this radial, motion that you have, and we see Coriolis forces in things like hurricanes and windstorms and all kinds of other things like tornadoes. These forces that travel around in a circle, and again, they give this apparent force by changing the radial position of an object that's rotating in a coordinate system. Again, neat, really, really cool. If you're going to do some kind of forces where the object would fly in different directions or something, the faster things went, then this would apply to you. But for the most part, we don't use this as an example in physics and games, for the most part. Sometimes we do, if you're making some kind of weird, like I said, tornado-like attack or something like that. Or you're trying to stay on a track, like you're playing some kind of train game and you're on a track and you're going to fly off and you have to control. But again, you can simulate that by saying, okay, I need to pull my stick to the left. If I don't pull my stick to the left, I fly off to the right and die. Like that's what you have to know. So knowledge of it is more important than actually baking the mechanic into the game to make it perfect, right? All right, and again, there's some examples here. Objects in the car do slide. You feel pushed to the outside of a rotating platform, and we talked about ocean currents and that kind of thing. The other type of fictitious forces in linear systems is when you're inside or outside of a system. And again, I'm not going to talk about too much. The math is here, but example, if I'm watching, some kind of object that's moving inside the reference frame of a vehicle that's traveling, then the object inside appears to be moving a lot faster when we look at it from outside the frame of reference. But when you're inside, I know. And when you're inside, it appears to be moving slower because you're actually accelerating with the frame of reference, right? So there's two pictures here, when I'm outside and when I'm inside. This is really neat, and I just want to talk about it briefly, not really test you on it or even ask you a question on assignment or exam. But the idea here is that, again, I'm in a spaceship and I'm traveling, I'm trying to approach the speed of light in a vacuum. Why do we travel faster than light? Because it takes an unlimited amount of energy to push us there. So says Einstein anyway, right? And so inside the frame of reference of the vehicle, let's say a spaceship, right, we don't seem to be moving very fast. But outside, we're like a streak of light, or something else. And why is that? Because, we've been accelerated, so our notion of speed has been taken away. A good example of that in real life is when you're traveling on the highway for a long time, right? In the beginning, it seems like you're going quite fast, but after a long time, hours of going, you get this idea of this, what do they call this? Highway hypnosis is what they used to call it back in the day for me. Like, see how Corey is he's suffering from highway hypnosis right now. This is actually using my hypnotic voice is causing him to just relax, right? And anyways, so he's so out of it. Anyways, but this highway hypnosis is really cool because it gets you. You're looking at a road, and the road's coming at you. And at the beginning, it feels like it's really fast. Afterwards, you know what? You have this feeling that you're not traveling so fast anymore. Meanwhile, you're going 130 kilometers an hour, right? So our perception changes because of this frame of reference, this accelerated frame, right? And what it means is that the way we perceive things, because we've been accelerated at that speed, is hey, we're not going so fast. But meanwhile, when you hit something going at 130 kilometers an hour, suddenly your frame of reference shifts, and now you're feeling the pain of the impact, right? Because of Newton's laws again. For every action is an equal and opposite reaction. So you're getting a lot of that energy. That you imagine if I'm traveling, I'm picking up energy. I'm exerting energy on the car to get me to 130 kilometers an hour. Let's say I'm speeding on the highway, right? And then I hit a truck that stopped, right? So I'm hitting an immovable vehicle, a movable object with like crazy force. It's going to crush me because what's going to happen is the force of energy that I'm exerting towards the front of my car is going to be reflected back at me. And that's why cars are designed to crunch up and the engine to kind of shoot forward or as opposed to shoot back towards you. Imagine if the engine came into you. Like older vehicle design, you got crushed by the engine when you hit. Nowadays, it doesn't happen. It goes actually down. The engine goes underneath the car, and it doesn't kill the driver in a crazy impact. So it's interesting how cars have been redesigned from that perspective. All right, I talked about making this short and sweet. I don't want to give you. I could have given you this lecture last week because these two lectures, Newtonian physics and circular motion, go together. Right? I'm not doing that. I split it up over 2 weeks because of this, because it's difficult stuff to understand. And I've got some great examples we're going to talk about in lab. One of them is a more detailed example about this idea of conical pendulum, how it works and how to calculate that. And I've kind of got we're going to talk about that in lab. The other one is, how about how fast I can spin? I'm spinning this issue. These examples come from the book, but we're going to cover them in lab, right? So at this point, I'm good. I'm going to let you guys go. If you have any questions from now until the end about your assignment, this is a great time for you to ask me before you get going on this. Lab, again, is going to happen at 5:30. So you have a bit of a break. But I want to talk about this stuff with you in class. I also want to review who you're going to work with. If you don't have partners, from now on, I want to, let's get people talking now, people who are here. Find yourself a damn partner, because I don't want you to be in the same position you were in last time we did assignment number 1, where you're like, I don't have a partner. So now is the time. We're here. Please don't run away on me. You might have questions for your assignment. I'm going to stop the video. Get yourself ready for assignment number 2 and your test number 2, which is going to happen not next week, but the week after, in the week of December 15th. All right. So before your assignment 2 is due. Any questions before we stop the lecture for the day? All right, that's it for me, guys. For those people who are going to see me in first lab, it'll be at 5:30. I'm going to be taking questions and anything around your assignment number 2 now.